Imagine a network that mimics the human brain, capable of learning, adapting, and making decisions. Welcome to the world of neural networks. Neural networks are computational models inspired by our very own brain's structure and function. They're essentially a series of algorithms that endeavor to recognize underlying relationships in a set of data through a process that mirrors the way the human brain operates. Just as our brain uses interconnected neurons to understand and interact with the world, neural networks use interconnected nodes, or artificial neurons, to process information. These networks, these brain-inspired models, play a crucial role in the realm of machine learning and artificial intelligence. In machine learning, they're used to create models that can learn from data and improve over time, much like how humans learn from experience. In artificial intelligence, they're tasked with enabling machines to solve complex problems that typically require human intelligence, such as recognizing speech, identifying images, or making predictions. But how do these neural networks work? What makes them so effective at these tasks? Well, they function through a beautifully orchestrated process involving layers of interconnected nodes, each processing input data and passing it on to the next. It's a fascinating process, akin to a digital relay race, where the baton of information is passed from node to node, layer to layer, until the finish line where we get our output. Understanding the inner workings of neural networks is like unlocking the secrets of a digital brain. It may seem complex, and indeed it is, but it's also incredibly captivating. It's a journey into the heart of machine learning and artificial intelligence, a journey that we're about to embark on together. So, ready to dive into the brain-like structure of neural networks? Let's get started. The fundamental building block of a neural network is a neuron, or node. Just like the neurons in our brain, these nodes are where the magic happens. They take in information, process it, and pass it on, forming the basis of neural networks. Each neuron has several components that make this processing possible. First up, we have inputs. These are the data points that the neuron receives from either the original dataset or the previous layer of nodes in the network. Then we have the weights. Think of these as the importance assigned to each input. The neuron multiplies each input by its corresponding weight to determine how much it will impact the final output. But what if all our inputs are zero? That's where bias comes in. It's a constant value added to the product of the input and the weight, ensuring that even if all inputs are zero, the neuron can still produce a non-zero output. Now, we've got a bunch of weighted inputs and a bias. What's next? We sum them all up. But hold on, we're not quite done yet. This sum is then passed through what's called an activation function. The activation function is like the decision maker of the neuron. It determines if the neuron will fire or not, based on the result of the weighted sum plus the bias. There are several types of activation functions, each with its own unique properties, but we'll dive into those in the next scene. Now imagine a multitude of these neurons, interconnected, with the output of one becoming the input of another. This is how they form layers within a neural network. Each layer transforms the data a little bit more, helping the network learn from the patterns in the data, and that's it. That's how a neuron, the basic building block of neural networks, operates. It's a simple concept, but when you have thousands, even millions of these working together, they can solve some incredibly complex problems. Just as neurons are the building blocks of our brains, they also form the foundation of neural networks. One of the first types of neural networks you encounter is the feedforward network. So, what exactly is a feedforward neural network? Let's break it down. Feedforward architecture is a one-way street. It consists of three main components: an input layer, one or more hidden layers, and an output layer. The input layer receives raw data, the hidden layers process this data, and the output layer delivers the final result. Imagine the input layer as the entrance to a grand maze, the hidden layers as the complex twists and turns within, and the output layer as the triumphant exit. The data enters the maze, navigates through the hidden layers, and emerges transformed at the output. Now let's talk about how data moves through this network, a process known as forward propagation. The journey begins at the input layer. Each input point is accompanied by a weight, which reflects its importance in the final outcome. These inputs and weights embark on the journey together, traversing the network until they reach the output layer. In each hidden layer, the data undergoes a transformation. The inputs and weights from the previous layer are summed up, and a bias is added. This sum is then passed through an activation function, which decides if and how that information should proceed. Let's consider a simple example. Suppose we have a network that predicts whether it will rain based on temperature and humidity. The input layer receives the temperature and humidity data. Each of these inputs is multiplied by a weight and then summed with a bias in the hidden layer. This sum is fed into an activation function, which determines if the conditions are right for rain. The result is then sent to the output layer, which makes the final call, rain or no rain. So you see, the beauty of a feed-forward network lies in its simplicity. It's a no-nonsense, one-way journey from input to output, with some intriguing transformations along the way. Feed-forward networks, although simple, play a crucial role in understanding the flow of data in neural networks. Activation functions are the heart of neural networks. These functions introduce non-linearity into the network, allowing it to learn from complex patterns and make predictions. There are several common activation functions used in neural networks. Firstly, we have the sigmoid function, which squishes the input values between 0 and 1. This function is especially useful in output layers of binary classification problems. Secondly, there's ReLU, or rectified linear unit. This function simply takes the maximum of 0 and the input value. It's loved for its simplicity and efficiency, often used in hidden layers. Lastly, we have the hyperbolic tangent or tanh function. Similar to sigmoid but with a range from -1 to 1, it provides a stronger gradient for backpropagation. The choice of activation function can significantly impact the learning of a neural network and its ability to converge to a solution. Remember, activation functions are the key to transforming the input data into a usable output. Training is where the magic happens in neural networks. Now, you might be wondering, what does training mean when we're talking about neural networks? Well, picture this. Training is like a virtuoso tuning a piano, adjusting the tension of the strings, or in our case, the weights, to achieve the perfect harmony, or to minimize error. The process begins with the network making a guess about the output. Then it measures how far off its guess was from the actual answer. This difference is the error. The goal of training is to adjust the weights in such a way that this error is minimized. But how does the network know which way to adjust the weights? This is where backpropagation comes in. Backpropagation is like a GPS navigator for our network. It calculates the gradient, or the slope of the error function, which points in the direction of the greatest rate of increase of the error. But we want to decrease the error, right? So we go in the opposite direction, down the slope. We adjust the weights step by step in the direction that reduces the error. Now, you might ask, how big should these steps be? Too small, and it'll take forever to reach our destination. Too big, and we might overshoot and miss the minimum error. That's where optimization algorithms come into play, with the most common one being gradient descent. It helps us find the optimal step size to reach the minimum error in the least amount of time. Just like training a new puppy, training a neural network requires patience and consistency. Each round of training, called an epoch, the network gets a little better, a little closer to the correct output. It's a process of trial and error, learning from mistakes, and gradually improving. So, in essence, training is the heart of learning in neural networks. It's a meticulous process of adjusting and readjusting, fine-tuning the weights until the network performs at its best. It's a journey of learning, growing, and evolving. Training is a rigorous process that fine-tunes the neural network to perform its best. So keep tuning, keep training, and let the magic unfold. When we talk about depth in neural networks, we are referring to deep learning. This is the practice of using multiple hidden layers within a neural network. But why add depth? The answer lies in the complexity of the patterns we want to understand. The more layers a network has, the more intricate patterns it can capture. Think of it like peeling an onion. Each layer you peel back reveals more about the onion's structure. Now, let's touch on some architectures of deep neural networks. Convolutional neural networks, or CNNs, are great for image processing, as they are designed to automatically and adaptively learn spatial hierarchies of features. Recurrent neural networks, or RNNs, on the other hand, excel in handling sequential information, making them a go-to for tasks like language translation or stock prediction. Deep learning is the next level in neural networks, enabling them to solve complex tasks. Neural networks are not just fascinating, they are also extremely useful. Let's delve into some of the key applications of neural networks that are revolutionizing diverse sectors. First up, we have computer vision. This involves teaching machines how to interpret and understand the visual world. Neural networks excel at tasks like image recognition, where they can identify objects within an image, and object detection, where they can locate objects in a scene. They're the reason your smartphone camera can recognize your face and why self-driving cars can navigate busy streets. Next, we have natural language processing, or NLP for short. Neural networks are helping machines understand and generate human language. They're behind the scenes when you ask your smart speaker a question, or when you use a translation app to read a foreign language. They're used for sentiment analysis, where they interpret emotions from text, and language translation, where they convert text from one language to another. Another significant application is in recommender systems. You know how your favorite streaming service seems to know exactly what you want to watch next, or how your online shopping platform suggests items that you might need. That's neural networks at work, analyzing your behavior and preferences to provide personalized recommendations. Neural networks are also invaluable in fraud detection. Banks and financial institutions use them to identify unusual patterns and suspicious activities, helping prevent fraudulent transactions and protecting your hard-earned money. These are just a few examples. Neural networks are being employed in countless other fields, from healthcare to agriculture, from gaming to climate modeling. They're helping us predict stock markets, compose music, even discover new drugs. The applications of neural networks are broad and varied, limited only by our imagination. They're transforming industries, making technology smarter, more efficient, and more attuned to our needs. As we continue to refine and develop these networks, who knows what incredible innovations we'll see next? Neural networks are transforming industries and making technology smarter and more efficient. Now, let's take a look at some of the challenges and considerations in working with neural networks. While neural networks are powerful, they also come with a set of challenges. Let's dive into them. One of the major hurdles is overfitting, where your model learns the training data too well. It's like studying for a test by memorizing the textbook word for word, but then struggling to apply the concepts in real-world scenarios. The key is to strike a balance between model complexity and its ability to generalize. Next is hyperparameter tuning. These are the settings of your neural network that you need to optimize for the best performance. It's like adjusting the ingredients in a recipe to get the perfect flavor. But finding the optimal mix can be quite a task. Lastly, let's talk about data preprocessing and normalization. Neural networks love clean, well-organized data. It's like having a well-stocked, tidy kitchen when you're cooking. It makes everything run smoother. Overcoming these challenges is part of the journey in mastering neural networks. With great power comes great responsibility. The same applies to neural networks. As we delve deeper into the realm of artificial intelligence, we must confront the ethical implications that come with it. One of the major concerns is bias within neural networks. Just as humans can be influenced by their surroundings, so too can neural networks. They learn from the data they are fed, and if that data is skewed or unbalanced, the outcomes can also be biased. This can lead to unfair and non-transparent decision-making. Another issue is privacy. Neural networks often require large amounts of data to function effectively. This data can include sensitive personal information, which, if not properly protected, can lead to breaches of privacy. Finally, there's the principle of responsible AI development. It's not just about creating powerful tools, but also ensuring they're used in a manner that's beneficial and fair to all. Ethics should always be at the forefront when working with powerful technologies like neural networks. We have come a long way in understanding neural networks, from grasping the basics of neurons, the building blocks of these networks, to diving deep into the intricate layers of feed-forward architectures. We've explored the crucial roles of activation functions and the art of training these networks through backpropagation and optimization algorithms. We've also journeyed into the realm of deep learning, where the depth of neural networks allows them to capture even more complex patterns. We've seen these networks in action, powering applications from computer vision to natural language processing, and acknowledge the challenges they present, from overfitting to data pre-processing. But most importantly, we've grappled with the ethical implications of neural networks, understanding the need for fairness, transparency, and privacy in AI development. And now, it's your turn. Dive in, explore further, experiment with building your own networks. Keep exploring, keep learning, and remember, the future of technology lies in neural networks.